So the AVL tree are a kind of the binary search tree which is height balanced. We are going from the binary search tree to the AVL tree just because my binary search tree can be skewed. Skewed maybe towards the left, maybe towards the right. And if you're going to perform any of the binary search tree operation in the skewed tree, complexity comes out to order of n. We were expecting it to be log n, but it is going to be order of n because the tree is getting skewed. So we need to apply a check such that the tree doesn't become skewed at any point of time, and the resultant tree will be the AVL tree. So AVL tree are the height balanced search trees wherein the balance factor of every node is either +1, -1 or 0. A balance factor of 0 means a node is perfectly balanced, means the number of nodes towards the left and the number of nodes towards the right are same. -1 means the difference between the left and the right subtree is just 1. Similarly with the +1 as well. Find the balance factor of any node. Balance factor of any node is actually equals to the difference of the height of the left subtree and the height of the right subtree. So I'll not say the difference, it is actually equal to height of left minus height of right. Suppose I have a binary tree like this. So in this binary tree, if I level the nodes, this node root at level 0, this is at level 1, this is at level 2. For this node, height of the left subtree is 2 and height of the right subtree is 2. Hence the balance factor of this node will be 2 minus 2 as 0. For this node, height of the left subtree is 2, height of the right subtree is 2. Hence the balance factor of this node will have a balance factor 0, obviously because there are no nodes towards the left and the right. If I consider about this node, the left subtree has a height 2, but right subtree is not existing, so the height of this node will be considered as the height of the right, that means 1. So 2 minus 1 means the balance factor of this node is +1. Fine. So if you have a node towards the left and we do not have the node towards the right, the balance factor will be +1. If we do not have the node on the left and we have the node on the right, the balance factor will be -1. Suppose I have a binary search tree like this. Now in this binary search tree, these nodes are at 0, level 1, level 2 and level 3. If I find out the balance factor of this node, 1, height of the right subtree, the 3 minus 3 is equals to -2, it means this node is unbalanced. According to us, according to the definition of the AVL tree, any node can have a balance factor of 0, +1 or -1. If a node has a balance factor +2 or -2, that node will be considered as unbalanced. And if a node is unbalanced, we will apply some mechanism to make it balanced again. That mechanism is actually the rotation. There are 4 types of rotations. The first one is, suppose there is a node 100. I insert 50 towards the left of this, and then I insert 40. Up to the insertion of 50 there was no problem, but the moment I have inserted 40, the balance factor of this node becomes +2. You can check it, the level 0, level 1, level 2. The balance factor of this node is 2 minus 0. The height of the right subtree will be considered as 0 because the right subtree is not existing for 100 node. So 2 minus 0, the balance factor of this node is 2. Balance factor of this node will be 1, 2 minus 1. and the balance factor of this node will be 0. So this node has got unbalanced. If you see with the respect to the unbalanced node, the insertion took place towards the left of left. So I am going to perform the LL rotation. For doing the LL rotation, the unbalanced node is rotated like this. It means unbalanced node is rotated like this. It means clockwise. So the result will be 50 becomes the new root, 40 is towards the left, and 100 is towards the right. Similarly, suppose I have an element 100, another element 150 is added. Up to this time, the tree is perfectly balanced, and then I have inserted this 200. Once we have inserted 200, this node becomes unbalanced. -2 becomes its balance factor. This is -1, this is 0. So since this node is unbalanced, I'll apply a rotation, and we see that the rotation took place towards the right of right. So if rotation is taking towards the right of the right, I will do the anti-clockwise rotation, and the result will be 150 becomes the new root, 100 comes towards the left of 150, and 200 comes towards the right of 150. Fine. Since the rotation that we have, so the element which was inserted with respect to the unbalanced node was towards the right of the right, this rotation is called the RR rotation. Now suppose I have a node 100. Towards the left of this, I have inserted a node 50. Fine up to now. Let's say we have inserted 70. So once we have inserted 70, this tree becomes unbalanced. The balance factor of this node becomes 2. -1, this 0. Now, this node is unbalanced and the insertion took place towards the left of right. It means I am going to perform the LR rotation. LR is actually a double rotation. So double rotation, in the double rotation, what we do? We rotate these elements towards the left. It means to anti-clockwise. The result will be 100, 70, and 50, like this. And then I'll perform the clockwise rotation, and the result will be 70, 50, and 100. So now the tree is perfectly balanced. So the LR rotation is a double rotation. It means first I rotate towards the left and then I rotate towards the right. Similarly, I have 100 element, 150 towards the right, 120 gets inserted towards the left of 150. This node becomes unbalanced. Its balance factor is -2. So with respect to the unbalanced node, the insertion took place towards right of left, left of right. It means towards the right and then towards the left. So rotation that we are going to perform is RL rotation. This is once again a double rotation, and in the double rotation, I'll first rotate towards the right, and then I'll rotate towards the left. Fine. So these are the 4 rotations: LL, RR, LR, and RL rotations. If you are with the LL rotation, suppose a right subtree of this node was already existing. Let's say this R. Right? SR, let's say subtree right. So if we are rotating this 100 node towards the right, then the place of SR has been taken by 100. So since we do not want SR to go missing, the node which has come towards the right of 50, I will make this SR I will apply this SR towards the left of 100. Right, I have taken it towards the left. Similarly, in the case of the RR rotation, let's say this subtree left is already existing. So when this 100 will come, here, 100 will be the place of SL. So we do not want SL to go missing, so we apply SL here. This is towards the left. I will apply it towards the right. Fine. Now let us try to write the algorithms for these rotations. Suppose I'm going to perform the left rotation. Left rotation means towards this direction, towards the left direction. Suppose this is X, this is Y. Fine. So let's say the name of the algorithm is rotate left. In the rotate left algorithm, only thing given to us is the X, the position from which I have to start the. I have taken Y at the right of X. So Y is taken towards the right of X. If the left subtree of Y is, let's say, Z, it means Z equals to left of Z. After the rotation, X will come towards the left of Y. So left of Y is equals to X. So X has come here. Now we do not want this Z to go missing. So Z will be set as the right of X. Since it is towards the left of Y, so it will be set as right of X. So right of X is equals to Z. After this rotation, the root of the tree has changed. Earlier the root was X, now the root is Y. So we need to return this root. The root is Y. Similarly, rotate right. It means towards this direction. Let's say this is X. So we consider Y to be towards the left of X. So Y is equals to right X. Now if the right of Y is already existing, let's say that is Z. So Z equals to right of Y. After the rotation, this X will come towards the right of Y. So right of Y, this is equals to X. And then since we do not want Z to go missing, so Z will be set as left of X. It is towards the right, so it will be set towards the left of X. And the new root is going to be Y. So we need to return this Y. We need to return this. So we now have the algorithm for rotate left and rotate right. Let us now understand the LL rotation. So for LL, given is the root node X. LL means the insertion took place towards the left of the unbalanced nodes. Let's say the unbalanced node is X. So what I will do? I will perform the right rotation. So rotate right, starting from X. Let's say done by this rotation of right rotation is T. We will return this T. So LL is nothing but rotate right. Similarly, RR, rotation took place towards the right of the unbalanced node. Let's say the unbalanced node is X. So we need to perform the rotate left operation starting from X, and T is a root. We will return the root node. Then let's say I'm going to write the LR rotation. So LR will be like this. Unbalanced node is X. Let's say the left of X is Y. Then I need to perform the left rotation starting from Y. This will return a root. This will return a root, and that root will be set as the left of X. There will be new root when we rotate this node Y. The new root will be set as the left of X. So left of X is equals to rotate left Y. And then I need to do the right rotation starting from X. So rotate right starting from X. And let's say the root returned is T. We will finally return this root as the yield of this LR rotation. Let us write RL rotation starting from X. Scenario is like this. We have to start the rotation from X, which is unbalanced node. Let's say Y is the right of this. So we need to do the right rotation for right rotation is starting from Y. So rotate right starting from Y. This will return a root. That root will be set as the right of Y. And then we will form the left rotation starting from X. And this rotation will return a root. Let's say that is T, and return this T. So these are the four rotations: LL, RR, LR, and RL. Let us take an example and understand how to build the AVL tree. Suppose AVL TRE is OK. Fine. So these are the keys which are to be inserted in an empty tree to form a binary search tree that is AVL in the nature. It means that is height balanced. So first node I am building is A, that is the root node. V is larger than this, so it comes towards the right, and the tree is balanced up to now. If we insert this L, it is larger than A, smaller than V, which comes towards the left of V. The tree becomes unbalanced. The balance factor of this node becomes -2. To the RL rotation, we need to do only RL rotation, and it will become balanced then. Means I need to do this first, and then so this tree has become balanced now. Let us insert T, larger than T, smaller than V. T comes towards the left of this, and up to this the tree is balanced. If insert R, it is larger than L, smaller than V, smaller than R, T. Now if we find out the balance factor of this node is -2, balance factor of this node is +2, +1, 0, and 0. You see, there are two nodes which are unbalanced. In that case, the nearest node with respect to the inserted node. So inserted is R. With respect to this, the nearest node is this. So we will do the rotation according to this. If you see, the insertion took place towards the left of left with respect to the unbalanced node. Hence, we will do the LL rotation. So if you do the LL rotation on this node will come towards the right. Means the tree is like this. which is balanced. Now let us insert this E, L smaller than L, larger than A, so it will come towards the right. Fine. If I insert I, less, larger than this, larger than this, I will come here, and this node becomes unbalanced. The -2 becomes the balanced factor. All other nodes are balanced. Only this node is unbalanced. The insertion took place towards the right of right with respect to this node, so I'll do the RR rotation. If I do the RR rotation, this node gets like this, and towards the right I have this. All the nodes have a balance factor 0. Now if I insert S, larger than this, smaller than this, larger than this, comes towards the left, towards the right of this R. Tree is balanced. O, towards the left of R. K, smaller than L, larger than this, this comes towards the right. And the tree is balanced. So this is actually the AVL tree. As you take up more question, you will come to realize that this condition also is coming in some cases, wherein if you rotate the element, if you rotate a node, wherever you're going to rotate the node, you do not want this to missing. You set it rule. If this node is the left of y, you will put it as a right of x, and if this node is right of y, you will put it as the left of x. Fine. So if you have any question, you can write in the chat window. So since you do not have any question, we are going to held up, and if you have any more topics that you want to study, type that in a